So today what we will be basically focusing on are few of the concepts that are required for doing the stress analysis or analysis of deflection for machine components. But before we actually go and start designing any machine components, we need to have some of the basics about what stresses are, what type of stresses do come when certain types of loadings exist, and so on and so forth. And today what we'll be basically covering is stress representation in 3 dimensions. So we will basically look at stress representation in 3 dimensions. Then we will look at planar stresses, which encompasses the various loading scenarios, which can be uniaxial loading scenario, bending, torsion, or combination of these three, any one of them. So we will see one specific example when we have a combination of the loads, this type of loads. And this type of loads will result in, excuse me, planar stresses. What would be important, or what the important part is that basically at which plane the stresses are acting, which is important to understand. So planar stresses, we will also try to cover concept about Mohr circle and principal stresses. So this is what I intend to cover in today's lecture. And the slides that are uploaded in the Beachboard do cover some of those concepts. They are basically taken from the material of the textbook. So if you read the textbook, you will actually get to know all this information. But I thought to actually go through these concepts in a paper format, so as to make sure that we are all on the same page. So having said that, let's see how we'd actually start with this stress representation in 3 dimension. But before we actually look at this, can I ask you guys, what do you mean by stresses generally?
Force applied over area.
Okay, so stress is force divided by area. This definition has something missing, and the missing part is that the area that we are considering is basically an infinitesimal area. So it is not just area, it's an infinitesimal area. So in the limit delta A tends to 0, stress, yeah, you can basically define as a force divided by delta A. Is it making sense, guys? So here what I'm making is an arbitrary shaped body. So it is a 3-dimensional body, and it has basically loads acting at different places. So it is F1, let's say it's F2. It's an arbitrary shaped body. It need not be any specific shape. And this is one specific section of that. And this is F3. And when I actually look at a specific stress in this body, we are basically looking at one specific point. Stresses are always defined at one point, and when I zoom that, I basically represent the stresses in a form of a 3-dimensional body. Does it make sense, guys? This is stress at a point A. Is basically is represented by this infinitesimally small body, and that small body has basically 6 faces, and each faces will have some components and some components of the stresses, and that's how the stresses are represented. So it is a 3-dimensional arbitrary shaped body, and it can take any, now it can be arbitrary shape body, and it can take the form of a prismatic body, which is a uniaxial bar. It can take the shape of a shaft, transmission shaft. It can take the shape of a simply supported beam that we have been learning for a very long time with a specific cross section. So this is arbitrary shaped body, can take any uniform shape that we come across. And no matter whatever the shape of the body is, if this body is subjected to forces or movements, so let's say there are movements also acting on this body, and this body is in static equilibrium. Static equilibrium, then we define the stresses as basically mathematically represented by the ratio of the force with divided by the infinitesimal area, with the infinitesimal area tending to zero. So that's mathematical definition. Generally, we do not go with this. We do not use the specific definition or specific limit. We basically do not use this limit a delta A tends to zero. We generally say that, okay, the stresses are represented on a three-dimensional infinitesimally small body using these components. And I believe we actually did this discussion in the previous lecture, where we actually saw that the first subscript represents the direction of the normal vector. And the second subscript represents the direction along which the stress component is lying. So if that is the case, can anybody tell me what would be the components of stresses on this face?
Would that be ZY?
So what will be the components?
Z and Y?
Yeah, so how should I basically mention? So let me actually tell you or help you that it has got one normal component and two shear components. And they act like this. So what is this component called as?
Professor, what are those? What does that say on the right side, on the at the base where the arrows are? Is that like Y, X, Y, and
This one?
yeah, that one and the other one. What is that?
This is tau, shear stress. So sigma basically means normal stress. Sigma is the variable which is a symbol which is used to represent normal stress component. Tau is used to represent shear stress component. Okay, so these are tau xz and tau xy. I hope you guys have gone through these topics in your 373. Am I correct, guys?
Yes.
Yeah.
It may be a while
Yes.
that you have been used to this. So generally at when did you take that course? 2 semesters back, 3 semesters back? Generally, what's the?
About 3.
3 semesters back. Oh, okay.
Yeah.
That's a lot of time basically have passed. Okay, so for each of these phase, remember what is this cube represents? Cube represents a point, a material point in an arbitrary shaped body. It can be a point on this bar, it can be a point on this shaft, it can be a point on this simply supported beam. Okay, so it can be this specific body, which is a very, very small body. It has got delta X dimension in the X axis. It has got delta Y dimension in the Y axis, and it has got delta Z dimension on the Z axis. So it is basically the area of any of the faces. So area of this face, which is shaded, is given by delta X times delta Y. So it is very, very small area, which is basically this area. So very, very small area we are considering, and this is basically representing the stress at one point. So whenever we talk about stress in a material, always remember that this is at one point. That point can be lie here, it can lie here, wherever uh, the requirement or wherever you need to consider whether the designer is interested to know about, the stresses basically are determined at a one point at wherever, and at, I mean, it can lie anywhere in the body. So it can lie this where this cross section, it doesn't matter where it is lying, but wherever it is lying at that point, the stresses are represented by this specific cube in Cartesian coordinates. Does it make sense, guys?
Yeah.
Yes.
Let me just share some of the chats. I'm just missing them. Deformables. Yeah, 373 again. Well, not again in the sense that we are not doing that whole 373 again, but we are doing that in a span of 2 lectures. So that's what we are trying to do. Okay. Okay, so this is basically representation of stress at one point. And as I was asking you guys, can you help me to figure out what will be the components of stresses which are lying along these arrows? So can somebody tell me what will be the stresses along this direction?
That would be sigma ZZ.
Okay, sigma ZZ. So let me actually randomly pick a student from the list of attendees here. How about David Perez? David Perez, are you there? Okay. Gage Scott. I hope you guys are present in the class, not just logged in, right? I'm hoping so.
Can you hear me?
Yeah, I can hear you now. Is this Gage?
Yes.
Good. So Gage, can you help me to figure out what will be the stress component when represented by this arrow?
Sigma ZY.
So I'm just asking Gates, or other guys can just listen to that. So you said sigma, what is that sigma?
ZY.
ZY. So you are almost there, except it will not be sigma, but it will be tau ZY. Okay. And the reason why it is tau, because in any phase, we have one normal component, and that component is called as normal stress. So this component is called as normal stress. And it is only one for each phase. So this is called normal stress. And it is basically called normal because it is acting in the normal direction. And for each phase, there is only one normal component. And there are other two components, which we call as shear components. So tau represents the shear stress. So it is tau. Now subscript ZY, you have correctly identified, it is tau ZY. So can you identify this one as well?
Tau ZX.
Perfect, tau ZX. Okay. So like this, you have three components of stresses on each one of these faces. How many faces do we have here, guys, in this cube?
We have 6.
We have 6. And if each one of these faces have got 3 components, then how many stress components do you get?
18.
18. But how many independent stress components exist? So let me tell you there are only 6 independent stress components. So they are not 18, but 6. And these are sigma XX, sigma YY, sigma ZZ, tau XY, tau XZ, and tau YZ. That's it. Out of which where these three are called as normal stresses, and these three are called as shear stresses. Okay. And the reason that I have only 3 normal stresses, even though I have 6 faces, that if you look at the face opposite to this, so if you look at this face and face opposite to that is the back face, on the back face, the normal component is acting away from, the positive direction would be away, and the component would be again sigma ZZ. Because the body is in equilibrium, so this cube will be in equilibrium. That means the stress that is acting on that face, the face which is lying at the back, is sigma ZZ going in the other direction. Does it make sense, guys?
Yes.
The
Yes.
same thing can happen for sigma XX and sigma YY. So instead of so many other normal stresses, you have only 3 independent normal stresses. Does everybody is getting it so far?
Yes.
Okay, how, and then we have to understand how we get only 3 shear stress components, even though it says tau XY, tau XZ, and so there will be so many. So let me actually write down how many you can see. So what will happen is tau XY and tau YX will be equal. So tau XZ, tau ZX, tau YZ, and tau ZY. They will be equal in magnitude and have the same, basically they mean the same. So tau XY and tau XYX will be just the same quantity. So it is just like tau XY is acting this way and tau YX will be acting on the top. If you do not get it, let me actually try to show you why they are equal or they have to be equal. So I'm not drawing any normal stress component. I'm just drawing shear stress component, and that too on one plane. So it is tau XY tau YX tau YX and tau XY. Okay, the way I am basically arranging, so I switch off all the other stress components except tau XY and tau Y. So we are just considering these stresses, tau XY and tau YX. So on this phase, the shear stress acting in the positive Y direction is given as tau XY. Now on this phase, the shear stress acting would be tau YX. Is everybody following these two descriptions? Why it is tau XY and it is tau YX?
Yes.
Is everybody following this description?
Yes.
Yes.
Yeah.
Yeah.
Forget about everything else. So it is just, I just told you to focus on these two. Is everybody with me so far? I mean,
Yes.
all of the class students.
Yep.
Yes.
Now, these are the faces which has got the normal in the positive direction. So we actually draw stresses, shear stresses like this. Now on the back face, which is this, the normal is on this face is in the negative X direction. So the rule is that positive stresses are acting on positive faces in positive direction. Or negative faces in negative direction. So this phase is a positive phase. Why I'm calling it a positive phase? A phase is called a positive when it has got a normal in the positive direction. This phase has a normal in the positive x direction. So it is a positive phase. This phase has a normal in the positive y direction. It is a positive phase. So positive phase, positive direction, that means positive stress component. Similarly, this is positive phase, positive direction. This is positive. I mean, tau xy will be positive shear stress. Now, if I go into the negative direction, negative phase means the phase which has got normal in the negative direction. So it has got an outward normal in the negative direction. So a negative phase and negative direction would be the positive stresses. So tau xy would be acting downwards in this case. Is everybody following what I'm saying here?
Yes.
Yeah.
Yes.
The same thing will happen for tau yx. Negative phase, negative direction. So that is what tau yx would like. So this is how the shear stresses are plotted or is represented. The arrows basically have some meaning. It is not just I arbitrarily make arrow like this. And it is one-sided arrow or only one arrow because it represents the shear stress. So shear stress is always represented by one arrow. And there is a specific, I mean, everywhere you will actually see the representation of shear is basically like an arrow, which is having only one, I mean, only half of that arrow you can see. So let me know if you guys are with me so far.
Yeah.
Yeah.
Okay, so in this specific body, if I say that for this body, my body is in static equilibrium means the summation of forces has to be 0 and summation of movement has to be 0, right? A body will be in static equilibrium if only if these two conditions match or these two conditions are satisfied. Then only the body is in static equilibrium. So this body, which is basically a very, very small point, it is basically representing a small material point. So I zoom it, I basically use a lens in here and zoom it out and basically representing this body, which is basically a point on an arbitrary shaped object. So for this body, for this specific point, the summation of forces equals 0, summation of movement equals to 0. So then the body will be in static equilibrium. So can you guys tell me whether this body is in static equilibrium? So how to basically write an equation for summation of f equals 0 for this case? Can you guys help me out? Okay,
What direction are we going to do it?
sorry?
Are we going to start in like a single direction, or are we going to do all the directions at the same
All
time?
directions, yeah, at a time. So let me actually ask a student randomly from here, from the class. So Fernando Alcala. Fernando. Okay, Ivan Herrera.
Hello?
Yeah, so am I pronouncing it correctly, Ivan?
Ivan?
Ivan, sorry. So Ivan, so can you help us to write this equation, summation of force equals to 0 for this body? So how can we write summation of force equals to 0?
So would we do the sum of the forces in the x direction first?
Perfect. So let's do that. Summation of fx. So in x direction, what would be the forces?
So it'd be tau yx
Okay.
minus tau yx.
Okay. So this is force and this is stress. Is the force and stress have the same units? Is it dimensionally correct?
No.
So what is missing then?
We're gonna have to multiply by the area.
Perfect. So what will be the area? This is, remember, this is delta z, this is delta x, and this is delta y.
So it would be delta x times delta z.
Perfect. So that's what you are missing. And you know what is this equals to?
0.
0. Perfect. So summation of fx equals 0. What is summation of f of y?
Positive tau xy,
Okay.
and then minus tau xy
Okay.
times delta y times delta z.
Yeah. And what that is going to be equals to?
0.
0. Anything else we need to consider from the z direction? Is there any forces coming out?
Would we consider the normal stresses as well?
No, we are just looking at this
Oh,
body.
okay.
There are no other stresses
Okay.
except these. So that means there is no z direction force, right?
Yeah.
That means this condition is automatically satisfied by this representation. Is everybody following it so far?
Yes.
You know that
Yes.
summation of force is equals to be 0 because this body is in equilibrium. Now, how about moment equals to 0? So let me actually ask somebody else now. Jared. Okay. Jessica. Lee. Okay. Miguel, Dennis. You guys are present, right, in the class? Okay, Sophia, Bashir. Okay.
Professor Jessica
I
said
think-
she's here, but her
Yeah.
mic doesn't work.
Probably some people don't have mics or something.
That's fine. We can start. We can work with the chat window. So Jessica is on. Is basically through chat window. Can you help us to write an equation for summation of moment equals to 0 for this specific body? So how should I write that? So when we have to take moment, let me actually help you out here. When we take the moment is about one specific axis or point. So let's say we are taking the moment about this axis. So what is going to be the movement because of this stress component acting on this face? Can you just give me one expression and write it on the chat window? And I will ask other guys to also work. Yeah, moment about z-axis. So I will also ask about the other students to work it out and see what that equation will look like for summation of m equals to 0. So movement about z-axis. So if I have to do movement about z-axis, I'm asking Jessica to help us to write out the movement expression for this specific stress component acting on this face. Yeah, force times distance of that force on the torque. Perfect. And the force is basically, we know it is tau yx. So if I am writing the movement equation for that, is tau yx, the stress times the area. Area is delta x times delta z. That is the area. That will be the force. Force times distance. Distance is this vertical distance, delta y. So that is the movement due to this stress component, right? Everybody is with me?
Yeah, that's correct.
Correct. And what will be the moment due to this specific stress component? It will be negative, because now if this is, if clockwise movement, if I am basically considering this movement is clockwise is positive, then the counterclockwise will be negative. So the counterclockwise will be negative tau xy times the area, that will be my force, which will delta y times delta z. That will be my force times perpendicular distance. Perpendicular distance is delta x, and that is what I'm getting it. Now I do not have any movement because of these stresses acting along the z-axis. So there is no movement arm for these forces due to these stresses. So I only have this image equation to work with. Now when I actually work with that equation, what do I see? I see that delta X, delta Y, delta Z is common, cancels out. And what I actually say is that to have this satisfied, tau YX needs to be equals to tau XY. Only then my movement will be 0. Does it make sense?
Yes, it does.
Is everybody with me so far? I mean, is there any specific question you guys may have so far?
No, we're good.
No, we're good.
Cool. Okay, so that is why I said that these are equal in magnitude, and that is why we have only 6 independent stress components. 3 of them are normal and 3 of them are shear. And this is what we call as 3D representation of stresses. So we remember we actually started with this concept, stress representation in 3D. So stress representation in 3D basically means that you must be aware about what are, for any point in a material, you have this representation in 3-dimensional coordinates. And for each of these face, which is a cube has got 6 face. For each face, I got a normal component and 2 shear components. Normal component and 2 shear components. So I don't need to worry about all 18 components because 3 times 6 is 18. I don't need to worry about 18 because I know there are only 6 independent stress components, 3 normal components and 3 shear stress components. Now, what is the use of learning this? The question will arise that why do we actually care about this? So we care about this because in design scenarios, when you talk about finding the stresses in machine components, whether it is a transmission shaft, whether it is a bearing, whether it is gear, whether it is simple screws, machine screws, or whether it is nuts and bolts, whatever component it may be, you have to deal with finding the stresses, and you have to find that whether the stresses are exceeding the failure limit of a material or not. So to understand whether the stresses are exceeding the failure limit, we have to first find out what the stresses are. Now in actual components, we are not dealing with 3D representation. So that is a good thing for us, because if we have to deal with all of these individual components, then it makes our life very, very difficult. So what as an engineers we do, we tend to simplify the situation. And we tend to simplify the 3-dimensional situation to 2-dimensional situation, which we call as planar stresses. So this is 2D representation. So the engineers tend to simplify the representation in 3-dimensional to 2-dimensional. How it is happening? So if you look at any of these, you will see that the stresses, if in any of these scenarios, are either in 1-dimensional case or in 2-dimensional situation. For example, if you have a simple uniaxial load. Okay, so the load is acting in one direction. For a uniaxial case, it's prismatic beam. Prismatic beam is uniform cross section. Then what happens that the stresses are only acting in one direction for a section which is perpendicular to that applied load. Yeah. Are you guys with me so far?
Yeah.
Yeah.
Yes, we are.
Yeah. So whether it is a simply supported beam like this, you will find that the stress representation is 2-dimensional. All of these examples are basically can be explained or can be, all the stresses in these cases can be defined in 2-dimensional representation. So why do we, or how do we actually move from 3-dimension to 2-dimension? So what happens if you look at this cube and you see it has got 3 dimensions, delta X, delta Y. Yeah.
I have to, sorry, I have to use the restroom really quick. This is Jose Robles. I'll be right back. Is that okay?
I'm sorry, I don't, so what you're saying?
I just have to step out for a little bit.
It's okay, you don't have to ask, you can always, so don't worry about it. So it's okay.
Okay.
If you have to leave or for any reason, that's okay, don't worry.
I'll be right back. Okay, bye.
Yeah, sure, no issues. Okay, so we have got delta X here, delta Y here, and delta Z here. Now imagine if delta Z is getting squeezed. So it is getting squeezed and squeezed, and eventually what will happen that you don't have any material left in Z direction. You only have a representation which is given by this. This is very, 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 very small. So this is your X, this is your Y, and the Z direction is getting squeezed, and you don't have any material left in the Z direction. So what happens then? The stresses are only acting in one plane. The Z component stresses just go away. Do you see what I'm saying? Z component stresses just go away because I don't have sufficient material in there. Are you guys following what I'm trying to say?
Yeah.
Yes.
Yeah.
So in this scenario, we actually only have two-dimensional representation. So let me actually write it down again. So if delta Z goes to 0, it basically becomes this. This is your what we call as planar stresses. Stresses basically are confined to one plane. So this is what we call as planar stresses. Stresses confined to one plane. Any questions so far, guys?
Not right now.
So just to relate it with a specific example, we basically deal with a very thin bar which is fixed at one edge, and I apply a load P. So when I'm looking at a stress at one point, generally the stresses are always defined at one point, but since this is prismatic, so at any point in this specific cross section, the stresses will be just the same. And the stresses for this specific cross section, if you remember from your basic courses in deformables, the stresses are, can somebody help me? What will be the stresses? How to calculate the stresses and what direction they will be?
You'd have your sigma XX. And your
Right? This is a cross-sectional area. So sigma XX is basically given by load divided by area. So that's it. And that is basically acting in the X direction. Now these specific subscripts are important in the sense that if you do not consider, or if you are not considering these specific subscripts, then you may not be able to combine or to consider the effect of different loads. For example, if I have a scenario where I have this P acting, and then I have a load acting from the top, and it is again fixed at this case. So if this is your X direction, this is your Z direction, and this is your Y direction. In the cross section, if I look at it, it is basically going to be Z and Y. Is everybody following with me or following what we are trying to see here?
Yeah.
Yeah, can you just slow down a little bit, Professor? I'm like having trouble keeping up.
Okay. So what I am saying here, that this is a specific bar which is fixed at one edge and a load is applied at the other end, free end. When that is happening, I can look at one point in this material. If I zoom it out, if I basically zoom this out, section out, then what I will get is this section is like this, isn't it? This specific section, I zoom out from the material. So it will basically represented by this stresses. Are you guys with me? Are you
Yeah.
getting what I'm trying to say?
Yes.
Yeah. And I purposefully change the coordinates to Y at the horizontal platform, and I mean in the horizontal direction, or out of the plane of the paper, or inside the plane of the paper, and Z on the vertical direction. And this is my X. Now, if I'm talking about stress at the top surface and stress at, let's say this is A, and stress at this surface, which is B, what planes are you going to consider while representing the stresses? So when you look from the top, from point A, you will basically see the plane like this. For point B, the plane would look like this. Let me know if you are getting what I'm trying to say here.
Yeah.
Yeah, this is stress representation for point A, stress at point A, and this is stress at point B.
Yeah, that makes sense.
Yeah.
Yes.
So in both of these points, you see that I do not need this specific representation in cube. I am just using just one plane, and that plane itself tells me everything about the stress, state of stress at that point. I don't need to worry about all these 6 faces and sigma xx, tau xy, tau xz. No need to worry about any of them. But instead, what I'm doing is I have simplified my description by saying that the stress at this point can be represented in a plane xz coordinate, and I only have to worry about sigma x because there is nothing else acting on it. Is everybody following what I'm trying to say here?
Yes.
Yes.
Yeah, that's perfect. That's very good. Now we actually move to this case. The same bar like this. And now I have the same scenario, same cross section. But now it is a bit different because now I have this load coming from the top and then uniaxial load coming from in the axial direction. So if I now zoom out or zoom in this specific scenario or this specific section, let's say, where this is your X, this is your Y, and this is your Z. Now I have this point A again, just like here, and I have my point B, just like here. Okay. So if I have to represent the stress at point A, I'm going to just look at what I'm trying to do and just see whether you agree with me or not. And let's not put max over. Okay. So I basically doing the same scene here, just like I represent the stress at point A like this. Similarly, I'm doing the stress at point A like this. But here, when I'm doing it, I found that I have got only sigma X, and there are two contributors now. One is this load P in the uniaxial direction. Another one is due to bending load. This is basically acting in a transverse direction, and this will cause the beam or cantilever beam to deflect like this. And when it's going to deflect, the top part will be under uniaxial stresses, the tensile stresses. Everybody agrees with me?
Yes.
Yeah.
Yeah. So whenever you have a combination of loads like this, you have a load like force acting from the top, which is a bending load. And this is your uniaxial load acting in the uniaxial axial direction. So you have axial load, you have a bending load. So this will cause bending. And this will cause axial, and this is in the axial direction, it will cause axial stresses. So because of this, you will get sigma x axial, which is the same as this one. But there will be additional sigma x that is going to happen because there is a bending coming. The shear load is acting from the top, and that will cause bending, and the bending stresses will be at maximum at the top part. Are you guys getting what I'm saying? So let me actually give the formula. So you may basically remember what we are doing here. If you remember, the bending stress is given by m times y divided by I. And if it is max, y is your h/2. This is your height, total height. So m, maximum bending moments, times h/2 divided by b, h³/12, where b is your width.
Can you move the paper up, Professor?
Sorry. This is not b. B is this.
Joseph,
Yes.
this is chapter in the book. This is
So
chapter.
this is, okay, let me tell you, this is chapter number 3, and I am not following any topic, any textbook, or I'm not following any slides. What I'm doing is I'm just trying to make sure that you are understanding the concepts. But this is basically taken from 373. This is taken from chapter number 3 of this textbook, and so on. So you probably will not see any of this discussion in any of the textbook or any of the slides. And just to make sure that you guys understand it, I will scan this and also upload in the Beachboard so you have the reference for what we are doing. At this point, I only ask you to focus on what we are doing and try to see if you understand. If you're not understanding it, please let me know and I will try to make it. I will try to explain again.
All right. Thank you, Professor.
Welcome. Are you guys, I mean, if you forget about B, point A, just look at point A, which is the top part. This is the point A and this is point B. So at point A, this will be the stress represented. Is everybody getting what I'm trying to say?
Yeah.
Is there something in this? Let me ask you this. I mean, to all the class, to all the students in this class, is there something in this that you are not understanding? Any variable, any symbol, any representation, any notation you are not understanding?
You're just pretty much breaking it up, right, into 2D like sections, I guess.
Not 2D sections. What I'm doing is I am basically representing the stresses instead of a 3-dimensional, but in 2-dimensional coordinates. So I told you that at any point is given by this. So let me go back to my previous page. I started with this body, arbitrary shaped body, and I said that stress at any point is given by this cube. And this cube has got 6 faces. It has got all different stress components acting on it. But what I'm saying now that instead of worrying about all this cube, you can very well consider that one of the dimension is squeezed to 0. That means it becomes a planar. It is confined to only one plane. You don't need to worry about the cube. You only worry about one plane. So that's what we are doing. So here, if I have to draw a cube, it will be a whole cube. But instead of drawing a cube, I am saying that the z direction is 0. So that means all the stresses are in the xy plane.
Okay.
Similarly for B, I am saying that all the material in the y direction is 0. So everything is in x and z coordinates. That's in x and z. Forget about any stresses in the y direction because I'm considering that I am only looking at very small material point at this surface, at this point, where the y out of plane, basically out of plane stresses are all 0. So the out of plane stresses at point B in the y direction. So all the y components are 0. Similarly, the out of plane component at A will be in the z direction. So all the z components are 0, only x and y components. So again, come back to our discussion. So if this is the representation given to you, if somebody has given you this sheet with this specific symbols and notation, is there anything that you are not understanding? Let me know and I will try to explain. Where your M is a bending moment, which is basically that if bending moment is, this is your x1, then bending moment M is force times x1. So this is your bending moment. Y is basically distance from the neutral axis. Actually, it should be Z, sorry, because we have Z coordinate on the top. So Z is maximum h/2. This is Z. So distance from the neutral axis, maximum distance, A is at h/2. So that is why it is h/2. And moment of inertia is dh³/12. B is the width. So this is your width of the beam. This is B, h³ height cube/12. That's what your I is. And this is your sigma x. Maximum sigma x will be happen at the point A. Is everybody with me so far or not?
Yes.
Yes.
It makes sense.
Why is it h over 2?
It is basically the distance from the neutral axis. So this is maximum is h over 2. So this is your neutral axis.
The neutral axis is in the center of the object?
Yes. For symmetric cross section, the neutral axis passes through the center.
Okay.
So neutral axis basically means where the bending stresses are all zero. Is everybody with me? And to physically make you understand, so may I know your name? I just missed what, who is speaking.
Lance.
Sorry?
It's Lance.
Uh,
Lance.
spell that out, please.
Lance.
Okay, okay, Lance. So Lance, if you see, this has got specific stresses. So what is the nature of the stress here?
Tension.
Tension. And what is the nature of stress here?
Compression.
Compression. So it is going from positive to negative. So somewhere it has to be zero, right?
Yes.
Exactly. And that point is called as neutral axis. Okay.
Thank
So
you.
positive, and this is negative. And there is some point in the middle where it has to be zero, from positive to negative. And that is what your neutral axis is. Does it make sense, Lance?
Yes, it does.
And for uniform cross section, the neutral axis passes through the center. That is why I took it as h over 2, which is basically from the center to point A is basically h over 2.
Okay.
So is everybody following it?
Yeah.
So that is for representation at A. Now looking at B, which is on the side. So remember, when it is only uniaxial load at point B, the stress representation was given by xz plane only, because it was only xz plane. The y components, all the stresses in the y component are considered to be zero, assumed to be zero, and only sigma xs was acting due to P, load P. Now I have P and force F acting on the transverse direction, or basically a shear load. So at point B, let me actually randomly pick a student, or let's say Lance. Are you there?
Yes, I am still here.
So can you tell me what will be the bending stress at point B?
I'm not sure. It's sitting on the neutral axis, so no, 0?
Yeah, it is sitting on the neutral axis, of course. Yeah. Then what is the bending stresses, normal stresses? 0, right? That's what you said?
Yes.
Perfect. That has to be 0, because when you plug in z equals 0, the bending stresses become 0 at B. So neutral axis does not have any stress. It is just 0. So when I look at stress at point B, there is no bending stress component. You see, the normal stress is only for due to axial. Here it is axial plus bending, and maximum of that, because point A is lying at the top. So maximum bending stress. But here point B, which is lying at the neutral axis point, there is only contribution due to axial stresses. There is no contribution due to bending stresses. Is everybody getting what I'm trying to say here? Forget about tau xz for the time being. Forget about this. You just consider the only part that is from here to here. The only thing is changing, that the stresses due to bending is becoming 0. So only thing that is remaining is sigma x axial. Are you guys with me?
Yeah.
Yes.
Yeah.
Yeah. And now I have put an additional component of stresses, which I'm calling a tau xz. And this is basically coming because this load is a shear load. This is causing bending, but this load will cause shear stresses, and shear stresses will be maximum at the neutral axis. It will be 0. It will not, I have not done anything here, because at point A, the shear stresses are 0. So if I remind you of the representation of the stresses, the shear stresses, this is X, this is Z. The bending stresses vary like this. So it is positive. This is negative. This is 0. This is the neutral axis. And the shear stresses will vary like this. This is tau max. This is 0. So shear stresses are 0 at the top and bottom, but maximum at the neutral surface. And the formula for getting that is shear force, which is times Q. Q is the first area movement, I times weight. So this is your F Q divided by IB, and RQ is the area movement, first area movement. So what the shear stress is, shear stress due to bending is that it will be 0 at the top and bottom, but maximum at the middle point where your neutral axis lies. So it is basically at point B, which is at the neutral axis, the shear stresses are going to be maximum due to bending. So that is why you have got these shear stresses. And I know that if I have one shear stresses, then it will be on all the four faces, because summation of F has to be 0 and summation of M has to be 0. So this has to be at all four faces, on all four sides, sorry, and it will be like this. And this tau x is nothing but this specific formula. So tau x due to bending is exactly FQ divided by I times B. Let me know if there is something that you are not, there's something that you are not following it, or you are just completely lost somewhere.
I just don't know, what does this like represent? This bending like chart?
It represents the shear stresses. So this chart, you are not getting this one?
Yeah.
Okay. So this says that when you have this load coming on the top, so it is basically saying that if you have a cantilever beam and for this uniaxial load, then what will happen? The top will have the stresses in the positive direction, the bottom will have stresses in the negative direction. You got what I'm saying?
Yeah.
And they vary in a linear fashion. So if this is your Z coordinate, then what happens that the stresses will be very much higher, maximum at the very top, positive, and it will be also way higher in magnitude at the very bottom, but in compression. At the bottom or at the middle, it will be 0. That's what this chart is showing.
Okay.
Are you getting what I'm trying to say?
Yeah. Yeah.
So, and what this chart is showing, that's a shear, how the shear stresses are existing in the cross section due to bending. If you remember that the bending will not only cause, okay, let me actually explain you in another fashion here. So for example, take the case of cantilever beam, and instead of one strip, I have different strips that are glued together. So basically it is the same beam like this, but they are different strips that are glued together. And now I apply load F. So under the application of load F, what is going to happen is that this strip of, this specific combination of strips will actually be bent, just like as a bending will happen. But you will see that each strip of this combination will have a different expansion, right?
Yeah.
If they are glued together, right?
Mm-hmm.
So happens that if I look at this strip, number 1 and number 2, this is number 1 and number 2, what will happen that between number 1 and number 2, they will have some sliding motion happening. So number 1 is expanding more, and number 2 strip, if it is not glued together, if it is not glued, number 2 would not have stick to number 1. It will basically slip off from number 1 if it is not glued in there.
Okay, because it's in compression, right? So it's gonna come in more.
Yeah, this will basically
wait, sorry.
This is tension. This will come more, and this will come less.
Less, yeah. Or sorry, it has less tension, more compression, pretty much.
Yes.
Okay, yeah.
You're getting what I'm saying?
Yes.
Now this is not separate, but they are glued together. So what will happen that there will be some type of shear happening between these two layers. So if I separate these two layers, there will be some type of shear stresses generating inside the material. You're seeing what I'm saying?
Yes.
So between 1 and 2 strip, there will be some sort of a shear. So this one, number 1 will basically feel a tangential load like this, and number 2 strip, this is number 1 strip. Number 1 strip will feel a shear stress like this, and number 2 strip will feel a shear stress like this, because they want to basically move at the same place. So eventually they will be together. So they will be basically in some sort of shear happening there between these two layers. There are some type of shear is happening just to make sure that they are deforming at the same manner. There is no gaps or there is no breakage in the material. So because there is no breakage in the material, there has to be some shear stresses between the layers.
Yeah. Okay.
Yeah.
Yeah.
And that is what this representation says, that at the very top, when you are at the top number 1, there is no material on the top. So there is shear stress at the top. So there is 0. But what will happen that at the middle, the shear will be maximum. The magnitude of the shear stresses would be maximum at the middle. And then eventually at the very bottom, again, there is no slippage happening between, and there will be 0 as well. So shear will be 0 at this place. Shear will be 0 at this place, but it will be maximum at the middle point. So that is what this chart is showing.
Okay.
Are you getting it?
Yes. Pretty much the second one a little bit, maybe can you explain it a little simpler? But I get this part where you're showing me how it shears.
So did you get this part?
Yeah.
Okay,
So,
let me continue with this. So what is the stress, shear stress at the top of this one, number 1?
The shear stress,
yeah,
would it be 0?
Yeah, it will be 0 because there is no slippage of the material happening.
Okay.
That is why it is 0. Similarly, when I'm at this bottom strip, what is the shear stress going to happen at the very bottom?
Also 0,
because there is no other material left. Nothing is nobody slipping. The slippage will happen at the middle level, and that is what this magnitude.
Oh, okay. Now I see it.
Okay.
Okay. Yeah, and then this is also right. This is why this is literally like why material breaks, right? Because
okay, so we will come to that. Okay, don't jump to that because we have to learn about the failure of the material. So we will follow that maybe in the next lecture. But at this point, are you getting the origin of the normal stress and the shear stress?
Yeah, and I just never seen those charts before. That's why I was so confused.
I mean, I'm sure you must have done that in your 373, but if not, then it's okay. I mean, you have to basically do some numerical problems and you will understand. But let me ask all the class, are you getting the origin of these stresses now?
Yeah.
Yeah.
Yes.
Yes.
I think so.
Everybody is with me. So now you see that you can, in one plane, if you have to represent the state of stress in a planar coordinate plane, in one plane basically is XZ plane, this is XY plane, you can represent the stresses based on the applied load. Now I have not said what would happen, let's say if I have a twisting load come on top of that, what is going to happen? So let me ask somebody from the class. So who got A in 373? So it's not like I'm leg pulling somebody. I'm just trying to see, who got A in 373?
I did.
Who got A in 373?
Got a B.
I got an A.
Great. So may I know your name?
Juliana.
So Juliana, so can you help us to say that what would happen if we have a twisting load in a material? So what type of stresses will come? Is it normal stresses or shear stresses?
It'd be shear stresses.
Perfect. So that's what we have for twisting load. So when we have a twisting, we only have shear stresses, and shear stresses will basically go through all the material. So if I have point B, the shear stresses will be, if it is like this, the shear stresses will act like that, then this, and so on and so forth. So everywhere the shear stresses will appear due to torsion, right, Juliana?
Yeah.
Yeah, so exactly. So again, as I was saying, it is not just for leg pulling somebody who has got A or something or not. I was just making sure that that this type of representation and this type of concepts you guys have seen before, because I believe everybody has seen it before. It's just like we need to come at the same page, so that when we are faced with some specific components or design components, we can apply those concepts as well. So everybody in the class agrees that if we have a twisting load, there will be shear component as well that will come.
Yes.
Yeah.
Yes.
Perfect. So now the question is, we will actually stop at this point. I'm not going to take further. I mean, we will actually take these concepts in the next lecture. But now the question arises that if you have this combination of stresses acting at point A, acting at point B, so which of these 2 points will fail first, right? Right? As a designer, you are interested in what? I mean, if I am a designer, I'm interested in knowing whether the material will fail at point A, or whether it will fail at point B, or whether it will fail at somewhere else. Whether it will fail at this section, whether it fail at this section, whether it will fail at this section, right?
Yes.
Yeah.
Yes, sir.
So that is what the whole thing objective for us as a designers are. I mean, in senior design class, we are just interested to know that whether we can design something to prevent the failure. So for us, it's important to understand where the failure is taking place. And when we have to determine that, we have to first determine what are the stresses that are acting. Now, after we get the stresses, the next step is how can we determine the failure of a material? So I will stop at this point and we will continue our discussion from this point onwards. And in the next lecture, we will see that how we, with this given scenario, there are so much combination of stresses happening. These are axial plus axial are adding together. This is axial, this is tau exit, this is shear stresses, how they can be combined together, and we can find something which will tell us whether the material will fail or not fail.
Is there problems that we can go over?
Yes, I'm going to assign a homework problem for you guys soon. So you will basically see that in the beach board probably by Wednesday or some, I mean, for sure you will get that. And then you can look at, but you can always read chapter number 3 and do all the solved examples. So that's my recommendation. All the senior design students, that if you really want to understand the basics and in-depth calculations of how the design is happening, please go through all the solved examples in Sheetless textbook. It is very, very, like, they have a lot of information and they have a lot of in-depth knowledge and they have a lot of knowledge and information in those examples. Any solved example that you can find, just go through them. And it will not be possible for me to cover all topics from the Sheetless textbook and all the solved examples. But what I will be doing is to go through the basics so that you can apply in any problem domain or any specific case. Is it sense?
So you said do the problems in chapter 3, Professor?
Yes, chapter number 3.
All of them? All the examples?
Yes, of course. Why not? There are too many?
I don't know.
I mean, yeah, you have to learn them. We have to basically go through them and solve them. I mean, the solution is in front of them. You just have to go through the solution steps and see what they are saying. Okay, I'm not asking you to do unsolved problems. I'm asking you to do solved problems that are solved in them, not the unsolved problems. Okay, any questions, guys, so far?
No. Okay.
So you guys are getting it. So, I mean, are following it, what we are doing or trying to do here?
I think once I go through the problems, I feel like I'll have more questions then. But right now, I just would like to practice through them first.
Okay, yeah. So I have not actually taken a specific case application. I will take that application in the next lecture, and we'll see that how all these scenarios will make sense, how this combination of bending load, twisting load, and this axial load will make sense. So let me actually tell you one specific application, and let's stop our discussion for today's session. So this specific scenario does happen in transmission shafts. So if you have a transmission shaft, like suppose it is 2 pulleys that are basically having some transmission happening to the belt drives. So this is basically a so my sketch is not very good, so please bear with me. My hand sketch is not that good. So what we have here is basically a motor, which is basically driving this smaller pulley, and this is spinning like this, which is a pulley here. The pulley is mounted on a shaft. Now shaft will have specific bearings. So it has got some bearings mounts at the end location. This is a pulley, and this is your motor, which is driving a smaller pulley. It can be a motor, it can be engine, it can be any source of power. This is a smaller driving pulley. So in this specific scenario, what we will see that this specific design case, when you have the spinning, you have the tensions coming from the belt drives, and this is a shaft that is spinning and driving a load. So I have not mentioned where the load is. So let's say the load is specifically a load that is being driven by the shaft. It can be a propeller, it can be a imagine that you have propeller blades mounted on the shaft, or you can have a gear that is mounted on the shaft, or it can be something else. So it is something that is there, which is basically extracting the torque that is being transmitted from the motor. So motor is delivering the torque to this transmission shaft, and transmission shaft is delivering the torque back to a load. Load can be any specific component that I have not drawn here. Yeah, are you guys with me so far?
Yeah.
Yeah, is everybody getting what I'm trying to say?
Yeah.
Yes.
Yep. Kind of, yeah. Professor, are you going to be, are you going to be posting this? Because it's a lot to take in all at once.
Yes, of course. I will scan them and upload that in the Beachboard.
All right, then thank you.
So this specific situation is exactly this specific case we are learning. So you have the axial load. Now the axial load may be due to, if you have a helical gear mounted on that, then you have axial load on the shaft as well, which is transmitted to the bearings. The bearings have to be, in that case, not simple ball bearings or roller bearings, but it has to be tapered roller bearings. So if you have a tapered roller bearings over here to carry the axial load, then you have the axial load, you have the twisting, and you have the bending load, because the pulley is basically getting stretched by the tensions on the wires or the ropes. So these are the tensions on the two sides of the pulley, and the pulley has got a specific radius. So basically we'll see that how we can consider this specific application and design or find out the stresses in our transmission shaft, and determine at what point it will fail or what is the minimum diameter we need for a given load application or given application based on what we have learned so far in this specific section. Now we have not gone much further beyond representation of stresses, but what we'll be doing in the next lecture is how this representation of the stresses can be converted into a Mohr circle, can be converted into finding principal stresses, and from their failure theories. And then we will come back to this specific application where we'll find what should be the minimum diameter of the shaft for a given load application. Is it making sense to you guys? Kind of.
Yeah.
Yeah.
Yeah. Okay, so that's the reason I did not mention this application earlier, because then it would be connecting this to this specific situation will take some time, but we need to go on a step. We need to follow some steps. So that's what we are learning now. So we are basically learning the stress representation. So let me actually recap what we did. We first see the stress representation in 3-dimensional coordinates. Then we did the representation in 2-dimensional coordinates, which we call as planar stresses. And we say that all the different types of loading, whether it is uniaxial loading, bending loading, or torsion loading, they can be represented by 2D representation of stresses. The next would be, how can we use that information and draw a Mohr circle and find principal stresses? And then we will use those as to determine the failure of a material. So that's what we are going to learn in this specific discourse or in this specific semester, I believe.